All right, this is where we left off with the last video. I was talking about that the mantle is made of what's called olivin. The liquid and the solid core of the Earth are made of iron and nickel, primarily iron and nickel, and the crust, which is you know mostly silicate rock, um, is that's the thinnest part. And remember, we haven't ever dug completely through the crust, right? If it starts at 12 miles, the thinnest part is 12 miles. Um, we have the furthest down we've gotten is a little more than seven miles. All right. Oh, this is what I was going to talk about is differentiation. All right. So what happens with because of gravity? All right. So gravity is the cause of differentiation. Um, you're going to find that the more dense material. So going back to this, the more dense material at the center, and then gradually it gets less and less dense until you get to the crust, all right, which is, of course, the a density of the average rock, which is about 3.3. Right, iron and nickel, it's around 8. And in fact, that's how when you do the overall density of the Earth, you get about 5.5. We'll do a calculation showing the density of the Earth. Um, yeah, I really want you to know how to do the density calculations. All right. So this is what is called differentiation, and there's a really good example. All right, remember this is just an analogy. All right, so again, the more dense material like iron and nickel end up at the center just due to gravitation, which is called differentiation. Undifferentiated, you have rock um, and more dense material, all throughout. All right, so let's start with some mint chocolate chip ice cream. That's a good. That's I always love this example. Okay, I'm always it makes me a little hungry. So mint chocolate chip ice cream. The mints are a little more dense than the ice cream, right? And let's say you take your ice cream out of the refrigerator and you leave it on the counter, all right? Which I've done in the past, mistakenly. And my wife asked me, "Well, why is this ice cream sitting here?" And of course, it's just because I forgot. But I can use an excuse like I'm doing a physics experiment, which she doesn't buy at all anymore. Maybe in the early parts of our marriage, she might have believed that. But at any rate, if you put some ice cream on a counter and you let it begin to melt, all right, so the ice cream itself starts to become more like a liquid. And so what's going to happen is the more dense mint chocolate chips, don't forget they're mint, um, end up at the bottom, right? But just because of gravitation. And that's the idea of differentiation. The more dense material will end up at more towards the center. If you're thinking about the entire Earth as because it's a sphere. Um, all right, so that's a good analogy. All right, now what is it that heats the Earth? Okay, we already encountered. Here, let me go back a couple of slides here. We know that the center of the Earth is extremely hot. It's hot enough, in fact, that um, this iron and nickel causes and the outer portion of it to turn liquid, right? And now why is that? Okay, so one reason is just the just the gravitational pressure, right? So here, let's make sure we understand this. Um, it's really two reasons. One is just the gravitational pressure. So let's say you have a lot of things hitting the very early Earth. I mean, nowadays, of course, there's still things hitting the Earth, but it's not quite as dramatic as these huge asteroids and things like that. Not things like that. Huge asteroids and comets in the very early stages of the solar system. We'll get into that a little bit later. But basically, as the Earth began to grow, so here, we'll go back to this picture right here, you have this tremendous amount of mass that's pushing down towards the center. And so the center just naturally gets hotter because just due to pressure, just all the gravitational force that's pushing down, crushing in all directions on all sides, because it's a sphere, that causes this to heat up. All right, so that's one reason. All right, so that's one reason that is, it's just gravity. Gravity is causing this thing to be hot. The other reason is that the interior of the Earth is actually made up of some radioactive material, actually a good amount of radioactive material. And as the radioactive material turns non-radioactive, which is what happens with radioactive material, over time it becomes non-radioactive. And when it does that, it releases heat. So this goes into also heating up the Earth. So two things, gravitational pressure and radioactive decay will heat the interior of the Earth. And that's been going on for a long, long time. This is actually a really good demonstration. It's kind of not quite obvious. This is showing you that the surface area to the volume, right, of like a cube versus a sphere. There is tremendous amount of volume inside of something that is spherical compared to if for example, if the Earth, of course it's not, but if the Earth was this cube, the Earth would have cooled down long ago. Like, the Earth has been around for 4.5 billion years as the entire solar system has been around. Now, in fact, we're about to talk about why we know what that number is. How do we know the Earth is 4.5 billion years old? And but once we talk about that, you'll see. But if the Earth was just a cube, it would have lost that internal heat long ago. Because the Earth is spherical, notice like the amount of volume is tremendous compared to its surface area, right? This is like 10 million times greater than its surface area. So the Earth effectively holds onto its heat pretty well. All right, so all right. So now remember, one of the reasons that the interior of the Earth is hot is because of radioactive decay. Now, there are different types of atoms out there in the universe, as you know. Now, some of the atoms have more neutrons, right? Remember, neutrons are the atoms are made of fundamentally three things, right? Electrons that exist outside the nucleus of the atom. They don't exactly go around in like a planet going around its star. That's we no longer believe that. We haven't for about 100 years since quantum mechanics came along. But at any rate, you have electrons. You have in the center of atoms are neutrons and protons. Now the number of protons make up what atom it is, right? For example, right? For example, carbon, right? Carbon is always 6 protons, without exception, right? There's no, if it doesn't have 6, it's not carbon, right? The protons. But it can have different numbers of neutrons. Normally, by the way, carbon has 6 neutrons. So, just normal stable carbon is called carbon-12. But there's actually another type of carbon called carbon-14. So that means it has 2 more neutrons. And that particular type of carbon is radioactive, right? So it's the neutrons, either too many or too few neutrons that make an atom radioactive. We understand that quite well. All right, so now carbon-14, as I just mentioned, it has what's called a half-life. Well, all radioactive materials have a half-life, and it's actually pretty easy to measure the half-life of things. That's an experiment you can perform in just about any freshman physics lab. It's very easy to do. All right, so carbon-14, when you measure its half-life, it's a little more than 5,000 years. All right, so carbon-14, to use that for dating things to figure out how old something is, that's wonderful if you have something that's maybe 5,000 or several hundred years old, or maybe even I would go as far as maybe 10,000 years old. You can use carbon-14 dating if that's what you're talking about. But to go back much further, you have to go into certain atoms that have really long half-lives. Like, for example, there's a type of potassium called potassium-40. Let's see. I think I have I gotta get out of this for a second, and I think I had it up on Wikipedia. Oh no, not there. Hold on. I'll try it. No, there it is. Okay, so potassium-40 has a half-life. It tells you somewhere of 1.25 billion years. Okay, so that's a well-known half-life. You don't have to wait 1.25 billion years to measure that. It's very easy to measure, relatively easy. I shouldn't say very easy, but we can measure the half-lives of different things. And so because okay, so here's how the story goes. All right, so if you start out with I'm not going to use this example, but let's say you started out with 100 potassium-40 atoms. The potassium-40 turns into argon, by the way. That's it always turns into some other. Sometimes they turn into other radioactive substances, like uranium turns into all sorts of radioactive substances, but eventually turns into iron 56. Just to let you know. But at any rate, the potassium-40 is really simple. It'll turn into argon, right? It's non-radioactive argon. And when you dig up, certain rocks, if there's some potassium-40 in the rock and you find argon, okay, so argon does not go into forming rocks, right? Argon is normally a gas, and it's not found deep in the earth. Where the argon came from is this radioactive potassium-40, right? The potassium-40 turns into argon. Let me continue. Let's say you have 1,000 atoms of potassium-40 after one half-life. Okay, so you got one half-life goes on, then half the atoms, that's why they call it half-life, half the atoms have undergone a decay. They've turned into whatever they're going to become. Like in this case, it's argon. And so, another half-life goes on, and then even half of those atoms that are still radioactive turn into the argon, and then after another half-life, even another half turns in. And so if you count the amount of potassium-40 that remains and the amount of argon that you find, you can literally figure out how many billions of years ago a particular rock formed. Right. And so we can do this with other, not just potassium-40, but we can do it with uranium. Uranium-238 has a half-life, it turns out, of 4.5 billion years. And we always find, you know, half and half